Hello everyone, welcome back. So far in this course, we've looked at a lot of techniques to use randomization to deal with scale in the context of data science. For example, we have looked at Johnson's Linden-Strauss lemma to reduce the dimension at the same time preserving pairwise distances approximately for a set of points. We have looked at hashing in the context of locality sensitive hashing. Where again we used randomization to make sure that you can perform approximate nearest neighbor search efficiently. So what we're going to do next is look at another algorithm where randomization will eventually help us, but this kind of goes into the heart and root of linear algebra in the context of data science. And for that, what we'll first do is do a very quick review of one of the most popular algorithms in data science, so to say. Most popular linear algebra based algorithm in data science, so to say, which is the singular value decomposition algorithm. Even in this course, I kind of alluded to this algorithm a little bit when we were discussing I guess the geometric interpretation of Johnson's Linden-Strauss. So I will again do a very short recap of this algorithm and then talk about why this is a useful algorithm in data science, and some issues with this algorithm and how potentially randomization can help deal with such issues, right? So that's going to be the flow of the lecture corresponding to singular value decompositions. Okay, so this is singular value decomposition. So what does it say? Well, I'm sure all of us know what SVD is. Let me just make it precise. So if you have a matrix A, it could be square, it could be rectangular. So let's say we have, in the context of data science, we'll think of this as our data matrix, where you have, let's say, m data points, each in d dimension. And if you arrange the data as rows where there are d columns which are features, then this naturally gives rise to a m cross d matrix, and we want to understand properties of our data, gain insights from it, and so on and so forth. And one of the natural ways to understand is in which directions is the data spread out, and a great way to do that would be to understand this singular value decomposition of this matrix. So what does singular value decomposition in general say is that you take any rectangular matrix m cross d, and you can decompose this as a product of three matrices, U, sigma, V transpose, where U is a m cross m matrix. Remember, A is m cross d, sigma is m cross d, and V is d cross d. Now, why is this a useful way to decompose? Well, the usefulness of it comes because of the fact that U and V are both orthonormal. U is an orthonormal basis for Rm, and V is an orthonormal basis for Rd, and sigma is just some bunch of scalars. So it is pseudo diagonal matrix. So where the diagonal entries are what are called as singular values, right? So if I have to think of, let's say we are in the setup where m is greater than d, that is, we have more data points than the number of features of each data point. So then how does this look like? Well, A itself is going to look like a matrix like this. You have 1 to m and 1 to d, more data points, and I mean d is less than m. And we are saying the singular value decomposition says that given any such matrix, you can write this as an m cross m matrix of column vectors which are u1, u2 till um, which is an orthonormal basis for Rm. And then on the other side we have v1, v2 till vd, which is an orthonormal basis for Rd. And then in between is sitting this m cross d matrix, which is similar to the dimension of A itself, where you have on the diagonal sigma 1, sigma 2 till sigma d, everything else is 0, everywhere else is 0, right. So this is an M cross D matrix, and this is of course D cross D. So then this kind of gives us a great way to understand what A as a linear operator does to vectors. Now if you take any d-dimensional vector, well, it's an M cross D matrix, so it's going to operate on d-dimensional space. V transpose D would just say that, you know, you're projecting D, I mean, or rather you're representing D in the basis of V, and then you are scaling in that basis each component by sigma 1 till sigma d. And now once you have done that, then you are trying to, you know, pad zeros, extra zeros wherever it's needed, because M is greater than D, and then you represent the resulting vector in U spaces, right. So basically, you can think of this as, you know, there are two important bases. One is in Rm, one is in Rd, and these are orthonormal bases, and all your matrix multiplication of a vector, right. So A times some vector V does is that it first changes the basis of V to suit the basis of, I mean, A times, let's say, W. So this is A times W would just be first doing V transpose W, which is representing W in V spaces, and then multiplying, scaling the coordinates with sigma and padding it with extra zeros, and then representing it in U spaces, right. So that is the effect of any linear transformation. So basically, you can think of any linear transformation is essentially doing just scaling, but you know, the scaling is happening only when you view it in the right basis, right. So that's what any matrix as a linear operator does, right? So that's what singular value decomposition tells us. Now it's so fundamental because it shows up in a lot of data science based algorithms. So one of the algorithms that it shows up that we would have seen even in the machine learning techniques course, if you had taken that course, is the PCA algorithm, which is the principal component analysis algorithm. So which tries to, you know, do dimensionality reduction of the given data set by linearly combining the features to find new representations which contain most of the information, rather information or variance in the data, right. So so if you remember PCA, so what would happen in PCA is you are given this A, which is in M cross D, and then, you know, you can think of it as a rectangular matrix, of course, but if you want to think of it as, you know, what you first do is you compute what is called as the covariance matrix of A, which would be, you know, in this case a D cross D matrix, because there are D features. What would happen is you would do this covariance matrix C, which would be something like, you know, sum over I equals 1 to M AI transpose, where AI is just the ith data point in D dimension. So this would, of course, I'm assuming here that the data is mean centered and so on, but roughly this can be, I mean, this is the matrix of importance. Of course, there is some scaling that you want to do. You want to divide this by M and so on and so forth. But essentially, what you get is a matrix out of A. If A is M cross D, then essentially the matrix that you're after is A transpose A, which is M D cross M cross D, which is a D cross D matrix, the covariance matrix. And then what you do is you look at the eigen directions of this covariance matrix, and those eigen directions give you, you know, important directions to work with, right. So basically, then you project each of your data points along these top k eigen directions, and only retain that information as opposed to the original data point, right. So in other words, instead of you know, a vector AI which is in Rm, now you are going to represent vector AI as AI transpose W1, AI transpose W2 till AI transpose WK for a suitable K, where W1 to WK are the top K directions corresponding to the top K eigenvalues of the covariance matrix. Now, the idea is that, so now we have kind of done a dimensionality reduction from Rm to Rk, and the advantage that we gain is that, you know, for a downstream task, maybe you want to do classification, you can do this dimensionality reduction, and you know, this works wonderfully well. So now the idea is that, you know, if you want to do this, then you want to get W1 through WK, which are the top K directions that you care about. And to do that, you can either compute A transpose A or the covariance matrix explicitly, and then you can look at you can compute the eigendirections of the covariance matrix. Or what you can do is you can directly try to find the singular value decomposition of A, and the corresponding singular vectors give you the covariance matrix. I mean, give you the exactly the same directions W1 through WK, and that is because, you know, if A itself is U sigma V transpose as per our singular vector decomposition, so then if I do A transpose A, then that's going to be V sigma U transpose, sigma is diagonal, so, you know, it transposes itself, times U sigma V transpose, and that would just be V sigma U transpose U, because U is orthonormal, U transpose U is identity, so this will be sigma times sigma, sigma squared V transpose, right. So which means that, you know, what essentially we are saying is that the matrix A transpose A, which you might be interested in, is in fact V sigma squared V transpose, where V is the right singular vectors of A. Now, this is also the eigen decomposition, right. So because what we have done is, if you think of this as a single matrix, then, you know, you have represented this matrix as a product of V some diagonal matrix, in this case sigma squared, and V transpose, which means that in the basis of V, this matrix looks diagonal. So that is the eigen decomposition. So this is in fact the eigen decomposition, and the columns of V are exactly the eigenvectors that you are after. So which is the W1 through WK, which are the orthonormal eigenvectors of the covariance matrix. Okay, so which means that you can use singular value decomposition to do PCA, right? So that's the point that I'm trying to make. Now the question is, how much time would it take to do singular value decomposition? Well, that depends on the that depends on the dimensionality of the matrix itself. So in general, if A is in M cross D, and M is larger than D, then, you know, if M is roughly like D, then you are going to take order of M cube to do singular value decomposition. But if M is much larger than D, then you know, the term that would dominate would be D squared. So the time you actually would take is MD squared. If D is like M, then it is M cubed. But if there is a significant difference between M and D, then, you know, if you actually calculate the exact time complexity of singular value decomposition, it's going to look like M times D squared, where M is larger than D. If D is larger than M, then this would be D times M squared, right. So the larger term contributes one term in the time complexity, the smaller term contributes a square, right. So that's going to be our time complexity of SVD. So let me note that down. Now this may be okay if D is small. Of course, we are assuming M is greater than D, but we might be in situations where M is also huge, D is also huge, and relatively M might be much larger than D, right. So D might still be too large, such that D squared is actually prohibitively large, right. So M is even larger. So now MD squared might be prohibitively large for us to perform, SVD at scale. So we may not want to do SVD directly to find our singular values and singular vectors. So the question is, can we somehow do it faster, right? So let's say that's the kind of questions that we are trying to answer, right? At scale, how can we do SVD? Right, so that's precisely the question that we want to tackle in this lecture. Okay, so just an aside, so PCA is just one example of where singular value decomposition is used. There are several other examples, especially in data science, of course, especially when the data has what is called as a low rank structure. For instance, in recommendation systems, you might have matrices to deal with. More examples, let's say, of SVD, right? So recommendation systems. So what happens here is that, here you might have matrices of the form. Let's say I have 1 to U, where U, maybe I'll call this M only, where M is the number of users. Let's say your Netflix or your some streaming platform, and then you have M different users in your platform currently watching movies, and then you have a lot of movies, right? So you have D movies. D is the number of movies now, and what happens is, you would, as a platform, you would want to recommend movies to users, and you have to do this recommendation based on some knowledge of which users like what type of movies. So what you may do is, you might contact a very small set of users for a pilot study or something like that, and then you can give them a bunch of movies, and ask them to watch the movies and rate them, right? So of course, the number of movies is too huge, right? So let's say there are tens of thousands of movies, and then the number of users is also too huge. So you cannot ask all users to, of course, watch all movies. You're going to ask a very, very small set of users to watch a very, very small set of movies, and what you are getting is ratings, right? So maybe you have some ratings for each of the or rather, let us think of it this way, that every user watches a small set of movies, right? So if the user doesn't watch any movies, then you need something more to recommend something for the user. So that's sometimes called as a cold start problem, and so on. But let's say in this simplified example, so every user watches a small set of movies where the user has rated, right? So when I these purple boxes that I am highlighting here are just mean that some number, right? So maybe this user says, well, this is a 5-star movie, right? So this is a 1-star movie, he doesn't like that movie, and so on and so forth. And now with this information, we would want to somehow somehow predict what might be the other values of this matrix which are missing. Because if I can do that prediction, then I know that this particular user, who has not watched this movie yet, would rate this movie as a 3-star or 3.5 star had he or she watched that movie. The user has not watched the movie yet, that's why that rating is blank right now. But then if I can somehow fill this matrix using the other information that I have in this matrix, then I would be able to predict the ratings of each user for each movie. And then, of course, when a new user, or when the user walks into the platform, logs into the platform, then I can recommend movies for which the user would potentially give high ratings, right? So, and that would, for me as a platform, that's a way to keep the users engaged, right? So because I want to give good content to the users. Now the question is, how do we do this, right? So how can we achieve do this? This is what is called as sometimes called as the problem of matrix completion, because you have an incomplete matrix with sparse amount of information available, and you would want to complete this matrix. Now, of course, this seems like an impossible problem, right? So because I know some values of the matrix, but how can I predict the remaining values? Well, it is an impossible problem unless you assume something about the structure of the matrix, right? So in other words, if we make some basic underlying assumption about what kind of matrices are we dealing with, then along with that structural assumption, given that some of the values are already available, now those values might give us information about the values which are not available. That's the hope, right? So, and what is the structural assumption that I'm talking about? And this assumption is exactly the same assumption that we would have in while doing PCA. So, what was the assumption in PCA, right? So, why is PCA a useful technique? Why does it do dimensionality reduction? There the assumption was that the data lies in some low dimensional subspace of the original dimension. The original dimension is D, and D might be much large, and what we are saying is that, though each there are m data points each in D dimension, we don't really have to work in D dimension, because the effective dimension of the data is only like a k dimensional subspace, right? So, so let me go to PCA and then again come back and say why this is the same assumption that might help us here. So just to pictorially represent this, so you might have 3D data, but that is each data point is in 3 dimension, but then maybe you have points which are all in some, let's say is the points are all in some plane, right? So sorry about that. Let's say the points all lie in this plane. Of course, this is a 2-dimensional plane, right? So now D in this case is 3 and M is in this case, I have drawn 6 data points, but the effective dimension is 2, right? So though D is 3, though each of these blue vectors is a 3-dimensional vector, because they all lie in this 2-dimensional plane, I potentially need only 2 numbers to represent each data point. So which means that I can find the basis for this 2-dimensional plane, and then project my data set onto this basis and only only retain those projections. That was the idea of PCA. But then the structural assumption that we were making about the data is that the data lives in some low dimensional subspace. Now if you want to translate that into a statement about A, the matrix itself, then the statement would be the matrix A is a low rank matrix or approximately a low rank matrix, right? So which means that the number of singular values which are non-zero are only small, right? So if you have m points in D dimension where m is larger than D, then you can potentially have D non-zero singular values if you do the singular value decomposition. But what we are saying is that because we are assuming the data lives in a low dimensional subspace, we don't really have D non-zero singular values, we only have much smaller, let's say some k non-zero singular values, right? So so that's the assumption, right? So the low dimensional subspace assumption translates to low rank of A. Now the same assumption also is useful in dealing with recommendation systems problem, right? So why is that? Because the question is, of course there are too many users and too many movies, but then when a user rates a movie, how is this user really going to rate this movie, right? So what aspects of the movie is the user going to really look at to rate the movie? Now if there are only very few aspects, let's say there are only k aspects the user actually looks at, right? So maybe the user is looking at what is the genre of the movie, maybe the user is looking at who's the lead actor in this movie, and so on and so forth. Maybe there are some k hidden features that a user subconsciously uses to figure out if he or she likes the movie or not, right? So now every user is going to rate each of these features differently, right? So a user, right? So now you can think of this as there is a user cross feature, right? So 1 to k, and then think of these as features, and every user has different weightage for each of these features. Some user is going to only go with the genre of the movie, right? So he or she would rate it as 5-star or 1-star based on, you know, what genre of the movie is, right? So maybe it's a comedy movie, I would naturally rate it higher than, let's say, it's a tragedy movie, right? So maybe that's user number 1. User number 2 might do it differently and so on, which means that the user has some weight for each of these features. And now when the user tries to rate a movie, now you can think of this as again the same features, but then now you have movies, right? So D movies. Now every movie is a column here, and now what we are seeing is that, well, every movie has some aspect of each of these features, right? So what is the genre, who is the lead actor, etc., whatever features we want to put in. Now this is how much of that feature is represented in this movie, right? Now this row here, the user cross feature row, says that how much does the user like each of these features. The feature cross movies columns tell me that how much of each feature is represented in a given movie. And now when I ask a user to rate a movie, the user is just going to do a weighted combination of the features of the movie using his or her own weights, right? So the weights, these row is specific to the user, right? So that is my preference, right? So I prefer feature 1 so much, feature 2 so much, till feature k so much, and the movies column is common for that given movie for all users, right? So that is how much of feature 1 is present in movie 1, etc., etc. So when you do a dot product of these two, you get a value, and that value can be thought of as a rating the user gives to the movie. Now though there may be 10,000 movies, there may be only 5 features based on which every user is rating these movies, which means that then what essentially we are saying is that, so if this is our matrix A, then we are saying this is, I can break this matrix into B times C, where B is the user cross feature matrix and C is the feature cross movies matrix, right? So A is M cross D, whereas B is M cross K and C is K cross D. Now what does this tell us? This tells us that the rank of A, if A can be broken as B into C, where B is M cross K and K cross D, and we are of course assuming K is much smaller than D, right? So there may be 10,000 movies, but then only 5 features, which K is 5, D is 10,000, much smaller. Now what does this tell us? This tells us that if A has such a factorization, then the rank of A is at most K, cannot be more than K, right? So because every column of K, right, so if you think of it, every column of K is some combination of the columns of B given by the columns of C, right? So now B has K different columns, and now every column of A is got by somehow linearly combining these K columns of B using the coefficients in C. So which means that there are only K essential potentially linearly independent vectors. You cannot have more than K linearly independent vectors because B is restricting the number of linearly independent vectors. Of course, not all of them necessarily have to be linearly independent, but at most there can be only K, which means that the rank of A is at most K. So essentially when we are thinking of a recommendation system and we are saying that, hey, there are only K linearly independent columns in A, then that means that, though this has D columns, there are only very few linearly independent columns. That, along with the fact that I know some of these values, now I can use some of these values that are already available, and the fact that there are only K linearly independent columns among all these 10,000 columns. There are only 5 linearly independent columns. I can put these two things together to develop algorithms which can help me complete this matrix. And to do that completion, again we will rely on the matrix completion methods, which we are not going to discuss in this course, but those methods will also rely on singular value decomposing A, right? Well, so it becomes more nuanced. Which A are you, are we doing SVD of? That depends on the matrix completion algorithm, the flavor of the algorithm that we are using. One way is to just think of these as zeros and then try to take the SVD of that and then use that SVD to do some more fillings of this matrix and then do an iterative procedure and so on. So, I am not going to discuss the matrix completion algorithm in this course, but it suffices to say that matrix completion is a very widely used technique for recommendation systems. Very practical algorithms exist for matrix completion, and most of these algorithms, if not all, rely on one way or the other on the singular value decomposition, and they all work because they make this low rank assumption on the underlying matrix that you want to complete. In PCA, there is nothing to complete, but you still want to do dimensionality reduction, and again you rely on low rank assumption. Here you want to complete the matrix, you still rely on low rank assumptions, and in both the cases we use singular value decomposition to get our job done. So basically all we have said so far is that, hey, there is the singular value decomposition, it's quite powerful and it shows up in a lot of practical data science based applications, some of which you have seen already, like PCA. The issue that we pointed out is that the time complexity of singular value decomposition is order of d squared, and that is huge, especially when m and d are order of md squared, and that is huge when m and d are large, right? So somehow can we do it faster is the question that we are asking. So of course the punchline is eventually going to be that you can use randomization to achieve this, but before we get there, let us kind of try to understand it step by step and see how we can potentially speed up singular value decomposition if we have some information with us in our hands. What information? I'll tell you now.